number has been rather less, but now things are getting better and better. And I'm so happy that Anirban is organizing this lecture by Shivavati Goswami, who is a very accomplished researcher, and I am very eagerly looking forward to hear her. Papia?
Yeah, I'm audible?
Yes.
Okay. So, on behalf of JP Institute of Information Technology and Nasi Delhi chapter, I welcome Professor Shubhabruti Goswami and welcome you all for the 12th lecture in series for the Women in Science. So, without delay, let me introduce Professor Goswami first. Professor Shubhabruti Goswami is an outstanding physicist. She is currently professor at Theoretical Division Physical Research Laboratory, Ahmedabad. She is a theoretical particle physicist specializing in neutrino and astroparticle physics. She is an elected fellow of all three science academies in the country, IAS, INSA, and NASA, as well as World Academy of Sciences. She has received several prestigious awards, including Humboldt Fellowship, J.C. Bose Fellowship, and Fulbright Nehru Academic and Professional Excellence Fellowship. Currently, she is the president of the Indian Physics Association. She is a strong advocate for women in science and previously chaired the Gender in Physics Working Group in the Indian Physical Association. So we are honored to have you with us today, and we are eagerly waiting to hear you, ma'am. So over to you.
Thank you, Papia, and my sincere thanks to Professor Ghatak and Anirban for giving me this opportunity to speak in this esteemed series, and especially, arranging a series by women physicists can inspire a lot of people. So I think I really congratulate you for arranging this series. So I will share it full screen, and because I am at home, I am just switching off my video so that there is no bandwidth problem. Can you see my slides?
This is full
Yes,
screen
yes,
now.
yes.
It's properly
Full screen.
viewable and
Okay,
properly
okay,
audible.
very good. So let me start then. And I would like to thank everyone who, after office hours at 7 p.m. have joined for the lecture. So I must thank all of you. So I made the title "Catch Me If You Can: Chasing the Neutrinos," and it's very difficult to detect the neutrinos. So I thought this title is very appropriate, and one needs really special arrangements, very special detectors, big detectors to catch them. And not only that, you try to catch them and they change their identity. So that way, I thought that this is a very apt title for this for the neutrinos. So I am from Physical Research Laboratory in the Theoretical Physics Division. Theoretical Physics Division has, have a particle physics group and condensed matter, and there are people working in collider physics, QCD. There is a group on machine learning and beyond standard model physics, neutrino physics. I work mainly on neutrino physics and also probing physics beyond the standard model from neutrinos. We have a PhD program. We also have a postdoc program and summer internship and master thesis and long-term projects. We organize a lot of seminar, colloquia, young physicist meet, etc. So I thought I'll give an introduction about PRL before I go to my talk. So neutrino is a fundamental particle, and it was postulated by Wolfgang Pauli in 1930. And Pauli wrote a letter which read like, "Dear radioactive ladies and gentlemen, I have hit upon a desperate remedy to save the law of conservation of energy. There could exist electrically neutral particles that I wish to call neutrons, which have spin half and obey the exclusion principle. I agree that my remedy could seem incredible, but only the one who dare can win. So I will come to why he had to write this letter, but the story goes that Pauli had to go for a party, and that's why he didn't go to the conference, and then he wrote a letter. But before I come to the reason of why he wrote the letter, I thought, because it's a women in lecture series by Women in Science, I would it struck me that when Pauli said radioactive ladies and gentlemen, and actually, what I read was that at that time during 1920, 1934, in Institute for Radium Research in Vienna, 32 women scientists, so that's about 50% worked. And in the Radium Institute Paris, about 47 women worked with Madame Curie, including Irene Curie. Here are some, like Marie Curie, we have all heard. Here is also Harriet Brooks. I just took some few photos, who was the first Canadian nuclear physicist. She discovered radon. Then Ellen Gladish, she measured the half-life of radium isotopes, and she's the first radiochemist of Norway. Lisa Meitner, we all know, she predicted nuclear fusion. So now we will come back to why Pauli has to write the letter. That was the time, in 1896, Henry Becquerel discovered radioactivity. And by that time, 3 types of radioactivity were known: alpha, beta, and gamma radiation. But there was a problem encountered in beta decay. So when the energy spectrum of the electrons were measured, then what was found was that, it has a continuous spectrum. And at that time, beta decay was known as a two-body process. So the energy of the electron would be determined by the difference in the energy between the mother and the daughter nucleus. So it was a problem, and people thought that maybe in the nuclear level, the conservation of energy principle is not valid. That's why Pauli didn't like it, and Pauli postulated that there is a particle, another particle, which he called neutron, which is carrying the energy. So he postulated beta decay as a 3-body process, so that can explain the continuous energy spectrum of the neutrino. And now we know that this is an anti-neutrino, and that help in restoring the energy conservation in beta decay. So Enrico Fermi gave the name neutrino, and the theory of beta decay. Neutrino in Italian means little neutral one. So neutrino was postulated to be massless or having very small mass. It was a neutral particle. It is weakly interacting. All this makes it very difficult to detect them. So Pauli said that, I have postulated something which can never be detected, and it was called the ghost particle. However, in 1956, 25 years after neutrinos were proposed, the neutrinos were detected, and this was done by Fred Rines and Clyde Cowan. They used antineutrinos produced in nuclear reactor. So this antineutrinos will react with the protons to produce a neutron and a positron, and the positron captures an electron to give 2 photons, and this neutron is captured by the cadmium captures and releases a photons. They have 3 photons in coincidence, which was a signal. So this story is also very interesting, that they were working for the nuclear bomb, and they initially thought that let us put this to some good use. And so they wrote to Pauli, and Pauli said, okay, that's a good idea, you can try. However, later they thought that nuclear, if they're using this nuclear fission reactions, nuclear bomb type of a setup, then that is like it is difficult to repeat that experiment, and they thought that the using neutrinos from nuclear reactor is a much better idea. And that worked. And in 1956, so that is 25 years. So that shows how difficult it is to detect a neutrino. Nobel Prize was given to Fred Rines in 1995. It's not given posthumously, so Clyde Cowan didn't get. Rines' Nobel lecture reads neutrinos from poltergeist to particles. So until this time, neutrino was a ghost particle, but after this discovery, neutrino really became a reality. So Pauli's neutrino is an electron type antineutrino. It is always emitted with an accompanying electron. And there are other neutrinos also, which was discovered. So in 1936, Anderson and Neddermeyer discovered a charged particle which they called muon, which has the same charge as electron but heavier in mass. So this was discovered while they were studying cosmic rays. In 1947, Powell and collaborators observed this decay chain that pion is going to muon and electron. So this was the dominant decay mode, that this pion is going to muon and electron. So pion can go to muon and electron, and it can also produce a neutrino. So then Nobel Prize was awarded to Powell in 1950 for his development of so for this discovery, he used photographic emulsion technique, and he was awarded Nobel Prize for his development of the photographic method of studying nuclear processes and his discoveries regarding mesons made with this method. So in this context, I wanted to mention two women hidden cosmic ray pioneers. One is Bibha Chaudhuri, who was actually in PRL. And I didn't know until a very long time that she was a scientist in PRL. I didn't know about her much. And she studied in Calcutta University, which is also my alma mater. So Bibha Chaudhuri, she was studying in Calcutta University in Rajabazar Science College, and then she worked with DM Bose in Bose Institute, and they worked on discovering this kind of particles from cosmic rays. So he went to the north of Bengal in Darjeeling. She went, and then they exposed photographic plates and they got some tracks, but they had less resolution, so it could not be the pion. But like it was a very path-breaking work, and they had few Nature papers on that. And Marietta Blau, she is a Austrian physicist, and her life story is really very remarkable. The kind of struggle she had, and she and her student Hertha Wambecker actually found the photographic plate emulsion technique for finding particles from cosmic rays. So they were the first to develop this technique, although the Nobel Prize was given to Powell. So then the question arose that, if we have the neutrino which is produced in the pion decay, then is it the same as the neutrino produced in beta decay? And in 1962, this experiment was carried out using a beam of 15 GeV protons in Brookhaven. Now, in this process, in this experiment, and some antineutrinos from pi minus decay hits a proton target, and the reaction is that they can either produce a muon or a positron. So if these muon neutrinos and electron neutrinos are same, then they will only produce positrons. However, what they found was 29 muons and no positrons. So that established that these neutrinos, which are produced by pion decay, are different from the electron type of neutrinos. So this was the first high energy neutrino experiment using accelerators. The earlier experiment was using reactor neutrinos, and this was the high energy neutrino experiment using accelerator. And they observed discharge in a detector called spark chamber type of detector. So this is the reaction that a pion produces a muon and it produces a neutrino, which was known as the muon type of neutrino. For this discovery, the Nobel Prize in 1988 was given to Schwartz, Steinberger, and Lederman, and the Nobel citation read for the neutrino beam method and the demonstration of the doublet structure of the leptons through the discovery of the muon neutrino, which was a crucial step to the current world view of particle physics, which we call Standard Model. So what it showed was that, there is an electron neutrino with accompanying an electron, and there is a muon neutrino accompanying a muon. So this is some kind of a doublet structure, and we know that in Standard Model we have this kind of structures. We also have a tau neutrino and a tau. So that was sort of a demonstration of this, and which had led to the the development of the Standard Model. So now we know that there are three types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Whether there are more neutrinos or not, that's a very crucial question in the present day particle physics, neutrino physics, and I myself work on it. These neutrinos are called sterile neutrinos. They don't have standard model interactions, but this is a very active field now. But the existence of three neutrinos are experimentally verified. So then the question is that where can we find these neutrinos? And actually we can find it from neutrinos can come from a large number of sources. The Big Bang, which produced the universe, and we have the cosmic microwave photons, also produced the cosmic microwave neutrinos, but these have not been detected yet. These are very low energy, but indirectly we know that there should be these neutrinos. There are neutrinos also produced from geoneutrinos produced from Earth's radioactivity. We talked about reactor and accelerator neutrinos. The sun produces neutrinos. We will discuss this. The supernova, when the star ends their life, then they also produce neutrinos. Cosmic rays in the atmosphere produce neutrinos, we have seen. There are also, there were conjectures that neutrinos were coming from galactic and extragalactic sources, and these neutrinos have span and energy of like 10 to the minus 2 electron volt to about 10 to the 15 electron volt. So they span a large range of energy, and average kinetic energy of air molecule is about 0.04 electron volt. So we can see that there are very high energy neutrinos are also possible. And in fact, in the last part of my talk, I will discuss the detection of such neutrinos by some experiments. So the question is that, if there are so many neutrinos, then why we can't observe them? And they are coming for free or from all these all these astrophysical sources. They are coming for free. So the waiter is saying there is no extra charge if there is a neutrino in the soup. So but we cannot see them because they interact very weakly. That's why it's often called the invisible particle. So it's like in the Harry Potter story, we saw that Harry Potter has an invisibility cloak. So neutrino is like that, it is because of its weak interaction, it remains invisible. And for that, one needs some special eyes, which are the neutrino detectors. So I said neutrinos are very weakly interacting, and to give you an idea, to stop a neutrino, one needs lead shielding 100 light years thick. For X-rays, it's like 0.24 millimeter. So one needs a lot of patience to do neutrino physics. And 100 trillion of neutrinos per second are going through the human body from all these sources. And if we have a very huge detector, you can see the size, comparative size, then we can have about 300 interactions per day. And also, one has to go deep underground to observe this, so that, because this is a very weak signal, so something else does not mimic this signal. And of course, one need to have some useful statistics. One need observations over a large period of time. The world's largest underground detector since 1996 is the Super Kamiokande detector in Japan. It uses 50 kiloton of water, and it uses the photomultiplier tube. So it uses the Cherenkov method. So a neutrino produces a charged particle, because we are detecting a neutrino by the charged particle it produces, like the electron or the muon. So they undergo Cherenkov effect, and then they produce signal in photomultiplier tubes. Super Kamiokande has about 13,000 photomultiplier tubes, and you can see Super Kamiokande scientists, as compared to the detector size, how small they are. And with such a big setup, they observe about 30 neutrinos per day. So then the question arises that, if it is so difficult to catch them, then why should we try to catch them? As I first said, that they are everywhere, so they are coming free, and they are carrying information from stars, and they are carrying information from stars. So so by that I mean that, because the neutrinos are very weakly interacting, a neutrino can come directly, say, from the sun or from some astrophysical object, whereas if a photon will get trapped, it will go in a zigzag path. The photon will interact with the matter, but the neutrino does interact with the matter, but it does very weakly. So, it can come straight before the photon, and so it can carry information of the star. And another thing is that they pose interesting puzzles, and we all like puzzles. So these are various reasons for that we study neutrinos. Now the neutrinos are, we know that, we need the heat and energy from the sun for life to survive, but this same process produces a neutrino also. And Hans Bethe proposed that we can study solar neutrinos to test the hypothesis of energy generation in the sun. So the solar neutrinos are produced by some chain reactions called PP chain or CNO cycle. The basic reaction is where 4 protons fuse to produce an alpha particle and a positron and neutrinos. And this, depending on which reaction chain the neutrinos are coming, there can be different types of neutrinos, like PP neutrinos, which have low energy, which are responsible for the solar luminosity, 8 boron neutrinos, which have high energy, and there are standard solar models which can calculate the solar neutrino fluxes. Now, when Bethe said, then Ray Davis in Homestake Mine in the USA, he planned this experiment that to detect the solar neutrinos and to see if the neutrinos predicted by the standard solar model match the observed neutrinos or not. So the reaction used was neutrino capture on 37 chlorine produces an argon and electron. So they used a cleaning fluid and they used 600 tons of that. So the way the reaction, the experiment happened was that they will expose this detector to the sun, and the count would be less than 1 every day. So they will expose it for a few days, and then they will extract the argon, and then they will study the radioactive decay of argon to count the number of electrons. So the number of neutrinos. So what they have to do is they have to expose it to some days so that which is less than the half-life of the argon. So they did all that, and that's why these experiments were called radiochemical experiments. So they had a chemical extract. They gave their first result in 1968, and they found that only 1/3 of the predicted neutrinos were coming. So at that time, there would be several reasons. The experiment is wrong, some people said, because, it is difficult to detect a handful of argon atoms extract that, so there may be calculations may be wrong. And another option was that solar electron neutrinos are getting converted to muon or tau neutrinos. So new experiments were planned to check this result. So I mentioned the Super Kamiokande experiment. The predecessor of that was the Kamiokande experiment using 5 kiloton of water. Super Kamiokande used 50 kiloton. So this used 5 kiloton, but the same detector. And this was a detector in real time. They used neutrino electron scattering reaction. And from the Cherenkov cone of the incoming of the charged particle, they can construct the direction from which the neutrinos are coming and also the energy. So they verified that these neutrinos are indeed coming from the sun, because for the chlorine experiment, it was just exposed. So one could not say that if they are coming from the sun, there are some other sources. But Kamiokande could do that. And so there was another experiment, gallium, which was also radiochemical, which used the PP neutrinos. But all these neutrinos confirmed the chlorine result, and they said that the observed flux of electron neutrinos is less than the theoretical predictions. This was called the mystery of the missing solar neutrinos, and it remained unsolved for 30 years. And this mystery was solved around, in the 2000 by the Sudbury Neutrino Observatory detector. So Sudbury Neutrino Observatory detector used, instead of water, it used the heavy water. So this was also, Cherenkov technique, but instead of the ordinary water, it used heavy water. So the question is, what is the advantage of heavy water? So that's how, different the problems evolved more and more. So the advantage of heavy water is that, there are two types of reactions that can take place. One is called a charge current interaction. So in this, a neutrino reacts with a deuteron, and there is a charge change. It produces two protons and an electron. This reaction is sensitive only to the electron type of neutrinos. But there is another reaction to which this deuteron is sensitive, which is where there is no charge change. So a neutron proton goes to a neutron proton and a neutrino is emitted. So because there is no charge change, it is called a neutral current. This is sensitive to all the three types of neutrinos. So now, if from the sun only electron neutrinos are coming, then these two reactions would have the same rate. However, if there are muon and tau neutrinos, then these two reactions would have different rate, and that is what this experiment found. They found 1/3 electron type neutrinos and 2/3 muon and tau neutrinos. So that established conclusively that the solar electron neutrinos are getting converted to muon and tau neutrinos. It also predicted, it also, proved one more thing, which is that, that the standard solar model calculations are correct, because standard, so when we were considering only the electron neutrinos, then it was less than the theoretical prediction. But when we consider all three flavors of neutrinos, then it was, all same as the theoretical prediction within the error bar. So am I audible?
Yes, it's fine now.
Okay.
Perfect.
So then it proved two very important things. One is that the electron neutrinos are getting converted to muon and tau, and another is that the standard solar model calculations are correct. So this is what is happening, that in the sun, I am having one flavor of neutrino. So this is not really the ice cream flavor, but this nu V, nu mu, nu tau are called flavors, although, we cannot taste them. But so it is like, supposing I have a chocolate ice cream. I am going from my university to my home, and on the way I buy a chocolate ice cream, and when I reach home, then it will get converted to vanilla and strawberry also. So that is the kind of thing is happening with the neutrinos, that neutrinos are propagating in mixed states, and then they are at the detector, we can get all three flavors. So for the sun, actually, the solar matter effect also plays an important role in this conversion. So that was the kind of explanation. And another place from where we found evidence that neutrino, one type of neutrino, is getting converted to another time was the cosmic rays. So the cosmic rays hits the air molecule to produce pions, as I said, and these pions produce muons and neutrinos. But pions, I told in the earlier slide that pions have two types of processes. One is a mu plus and nu mu, and another, this mu plus. So the pion produces mu plus, and the mu plus can produce E plus, nu mu bar, and nu E. So if we consider naively this decay chain, then we should get a 2:1 ratio of the nu mu and nu E. But the Kamiokande experiment, which was observing the solar neutrinos, they could also observe the atmospheric neutrinos, and they did not observe this. But I wanted to tell here that, one of the first detectors of atmospheric neutrinos was in the Kolar gold mine in India in 1965. So atmospheric neutrinos have a large energy range, 100 MeV to TeV, and they have a large path length. So these are the downgoing neutrinos which are not passing through Earth. They pass about 15-20 kilometers, and these are the, upgoing neutrinos, so-called, which pass through the Earth, and they have path length of the order of 10,000 kilometers. So they provide a broad L by E band to study neutrinos. And the Super Kamiokande detector, which was the successor of the Kamiokande, it found that the atmospheric muon neutrinos are getting converted to tau neutrinos. So this blue is their expected number of event without oscillation, and red is their data, and green is if we take this conversion nu mu to nu tau, then this conversion, if we include this conversion, then that fits the data very well. And you can see that these are the downgoing neutrinos which are going through 20 kilometer. So they don't have enough distance to get converted. But these neutrinos which are passing through 10,000 kilometer, they have enough distance to get converted. And so that sort of also said that the nu mu's are getting converted nu taus, and this is the process. This process was called is called neutrino oscillation. And the Nobel Prize in 2015 was given to Takaaki Kajita and Arthur MacDonald for discovery of neutrino oscillation, which shows that neutrinos have mass. And this is very important because, you know, in the standard model of particle physics, we don't have any neutrino mass. So the neutrino mass says that we have to think beyond our standard ideas. So this oscillation, when we study oscillation, then we consider neutrinos as waves. So they interfere while propagating and we get oscillation patterns. So this is kind of a ballet dance of the neutrinos. So, you know, this is simple quantum mechanics. It's quite easy that when a neutrinos have mass, then they are produced as superposition of the mass states. So these are flavor states which are produced in weak interaction decay. So the pion decay produces a nu mu, but it is actually a superposition state, a superposition of the mass states. These nu light and nu heavy are states of definite mass, and theta is the mixing angle. Now we have to see how does the superposition of mass states evolve in vacuum. And as the neutrinos travels with energy E, the heavier part will fall behind and the lighter part will go ahead, and that will give rise to a phase difference. And as a result, whatever proportion was here, which gave me a nu mu, will be changed here. So I will not get the nu mu, but it will be a mixture of nu mu and nu tau. So it is very easy to calculate the probability of oscillation. It is very simple quantum mechanics. So what one has to do, one has to see how this time evolution of the mass states, and because we take they as relativistic, so we can do this approximation. This treatment is in the plane wave approximation, where we take the both states to have the same momentum. So one can see how a flavor states evolve at a later time. And because M1 is not equal to M2, the E1 is not equal to E2. So although we start with a nu E state, we at time t equal to, at a later time, we won't have a nu E state. And one can just calculate the survival probability, and the conversion probability will be 1 minus this, because this mixing is usually we are taking as unitary, and so the probability is conserved. So this theta determines the amplitude, and this delta m square dependent term determines the phase. So this delta m square is the mass square difference between the two neutrinos, and theta is the mixing angle, L is the distance traveled, and E is the neutrino energy. So you know, neutrino oscillation can probe these parameters. It is governed by the mass square difference of the neutrino between the two neutrino propagating states and the mixing angle. So this can be generalized. Now we know that there are 3 neutrinos. So this can be generalized to 3 or more neutrinos. And those kind of things are done. So we have oscillation evidence already. I discussed solar and atmospheric. However, later we also had confirmation of these oscillations from reactor neutrinos and accelerator neutrinos. So there are a lot of studies which are done from oscillation experiments. Oscillation experiments can determine the parameters governing the oscillation, and that gives us clue about neutrino properties, and that can lead us to, you know, what kind of beyond standard model physics we want. there is a lot of effort on to determine the rest of the parameters. So it has not determined all the parameters. 3 major parameters are left yet to be determined. And so these are the current oscillation, and some future experiments are planning that. And one can also test some extra interactions of neutrinos, some kind of violation of fundamental symmetries, because these are very small effects, and one can probe very small effects in oscillation experiments. So these kind of studies are going on. Also, there are now, because it's the quantum year, I thought I will mention that people are also studying, testing foundations of quantum mechanics through neutrinos. So although neutrino oscillation has given us a lot of information of the neutrino, about neutrino mass and mixing, there are many unsolved issues. One is how neutrinos get mass. Fundamentally, that is not very well known, because in the standard model, it's massless. Then oscillation experiments determine the mass squared difference, but it doesn't say us what is the absolute value of the neutrino mass. It does not explain how the mixing angles arise. It determines the values, but how they arise, no. There are also some theories where people say that neutrinos can be their own antiparticles because they have no charge. They are neutral particles. That also is not known. I mentioned that if there are more than 3 flavor neutrinos, and all these need going beyond our standard ideas. And these are all, research that is going on in the field of neutrino physics in all these topics. So after neutrino oscillation, I will come to another very interesting area of neutrino physics research at this point, which is the multi-messenger astronomy and how neutrinos can contribute to it. So multi-messenger astronomy is detecting astrophysical objects in more than one signal. So, for instance, I talked about cosmic rays. We can we know photons. There can be gravitational waves, and neutrinos. The advantage of neutrinos is that neutrinos have no charge, so they don't bend in the magnetic field, so they can point back to the source, and they can arrive directly from regions from where light cannot come, as I mentioned earlier. So apart from the solar neutrinos and atmospheric neutrinos, the Kamiokande detector actually also detected some neutrinos from the supernova. And supernova is the, when stars of certain mass range die, they explode as a supernova, and in that 99% of the energy is released in the neutrinos. So the neutrinos help the supernova explode, and they arrive 10 hours before light, so they can serve as an early warning system. So in 1987, in February, there was a supernova which exploded in the Large Magellanic Cloud, and the Kamiokande detector I accidentally discovered few events from this supernova, and there were 2 other detectors also which recorded these events. Now, they did not plan it, but it was a serendipitous discovery. But with those few events also, many information could be retrieved, and it confirmed the supernova cooling by the neutrinos. And the 2002 Nobel Prize in Neutrino Astronomy was given to Ray Davis from the Homestake collaboration, and Masatoshi Koshiba from the Kamiokande collaboration for pioneering contribution to astrophysics, in particular the detection of cosmic neutrinos. So the Nobel citation rate, the work of Davis and Koshiba, has led to unexpected discoveries and a new intensive field of research, neutrino astronomy. So, we can observe the same astronomical object through different messengers, for instance, and then we can get different pictures. For instance, if we see the sun in visible light, we don't see much structure. But as we go to, say, from radio emission, infrared, UV, X-ray, we can see different kind of structures. So this is sort of a neutrino image, because neutrino can probe the core of the sun. So that is the concept of multi-messenger astronomy, that you use different messengers to view the same object and get different complementary information. And so I talked about, when I talked about the neutrino sources, I said that there are very high energy neutrinos and few are detected. And these neutrinos can come from, unknown astrophysical sources like active galactic nuclei, or like gamma ray bursts. And gamma rays are observed from these. Now the question was, do they emit neutrinos? And scientists thought about how to catch these neutrinos, because as we go to very high energy, they are coming from much farther. The flux is much less. And then the idea came that, from in Kamiokande, we are using or Super Kamiokande, we used the water. Why can't we use the ice? And that led to the ice cube detector at the South Pole. So here what happens is that, so here the ice is used as a detector. So this is kind of a kilometer cube detector and a gigaton mass detector. So here is the ice top and here is the ice cube lab, and there are stations with Cherenkov detector tanks and optical sensors, and this is the ice cube array. So they hang these strings which contains the digital optical modules, which are the active detector element. And you can see this is the Eiffel Tower. So so it is technologically it's quite challenging to put these detectors through the ice, but IceCube has done that. And the way it detects the neutrinos is that when a neutrino interacts with the Antarctic ice, it creates other particle, like it will create a charged particle, and this will travel to the detector, and then IceCube, these detectors will be hit, these digital optical modules, and then they will generate the event. So this is the kind of path of the particle through detector, and the color indicates arrival time. So red is arriving first and green is last. So this is how the particle is going. It is hitting these detectors, and and it is using the Cherenkov technique. When the charged particle pass through a medium, they are using that same technique. So IceCube observed the highest energy neutrinos from, this is like 10 to the 15 electron volt, from distant astrophysical objects, first time in 2013. They were naming them neutrinos as in names of comic character Bart and Ernie, Big Bird, etc. So, but initially they did not know they are coming from which sources and whether there is any correlation with any gamma ray emitting source or not. But this correlation between a high energy neutrino source and a fairing blazar was found in 2017. So this blazar was detected by the Fermi and the MAGIC telescope, and they could correlate the IceCube high energy neutrino event, and that initiated the era of multi-messenger astronomy. And another detector has recently observed such a neutrino, and which is a neutrino. So this was the IceCube used the ice, water in the form of ice, and this detector uses the seawater. So this was proposed in 1960 in one of the international conferences on high energy physics, and it said, we propose setting up apparatus in an underground lake or deep in the ocean in order to separate charged particle directions by Cherenkov radiation. So this cartoon came in New York Times, that a normal astronomer goes up, a neutrino astronomer goes down underwater in the mines, like Super Kamiokande and Snow was in the mines. So there are two detectors now. This is the KM3 net at the Mediterranean. One is the oscillation research with Cosmic in the Abyss. They want to catch atmospheric neutrinos. So this is called ORCA. And it is in France, and they have 7 megaton mass. And another is the ARCA, which is the astroparticle research with Cosmic in the Abyss. They are catching astrophysical neutrinos, so they can catch very high energy neutrinos. And this is in Sicily, Italy. They have a higher mass. And this detector, this cartoon says that the KM3 net deep water telescope detects the flashes of Cherenkov light from neutrino detect interactions. And so this is asking, how do you know you aren't just seeing bioluminescent fish? So this person is answering, Cherenkov radiation is only emitted when exceed the local speed of light, so it can't be produced by undersea life. However, when they were setting up the detector, they had to go to some biologically quiet area so that, the signals are not disturbed. So this is how they are doing the detection. They also have these strings of arrays, and this is their uh, detector, and they have these neutrinos hit the detectors and the signal is recorded. So last year in February, this KM3-net ARCA detected the highest energy neutrino event, which is like PV. So this is more than the IceCube neutrino event, and it was reported in 2025, and it led to many questions that whether it is of astrophysical origin, can it be coming from the galaxy, why IceCube has not observed it. So this is also a very active field of research at this moment. So there are a lot of exciting results which are expected to come from many experiments. So I would say that the excitement is not yet over, and we should stay tuned. Neutrino physics is having a lot of experiments. So it is driven by experiments, as I tried to explain. And so we are expecting that there will be some of the expected results will be confirmed, but some of the unexpected results will also come, which will lead us to new path. So because Anirban told me that to tell something about, the journey and, to inspire people. So I thought that I will show these two articles which was based on my biography. First one was the biographical essay in the famous Leelavati's daughter, which was brought out by the Indian Academy of Sciences, Ram and Rohini. And I want to acknowledge here, Rohini asked me to give my autobiographical essay in this, and I was really busy. My daughter was very small. I was not finding time, and I was not giving. Then Rohini one day asked me, Shrubhavati, are you busier than me? So, Rohini Godbole, I hope all of you have heard of her. She was, world famous scientist, and, as a woman, she has done a lot, not only in India, but globally. So she is a global role model. And she asked me that, do you think you are busier than me? And then I thought that, I cannot be busier than Rohini. So then I wrote it, and I'm really happy because, Leelavati's daughter is kind of a history. And so my article there was called A Tale of Two Lives. And why I called it was because I was facing an immense conflict between my career and my, my family life, because my daughter was quite small, but I was not getting job in the same place where my husband was there. And even with a postdoc, they were creating a lot of problem. I am in PRL now, that is PRL, and I am the chair of the PDF committee now, but I really struggled with my PDF tenure in PRL. So I called it A Tale of Two Lives, that how I balance it. And, at that time, I was not even sure if I can continue in physics or not, because it was a very tough period. I didn't have a job, and I could not give as much time with my daughter as maybe I should have. So it was really a tough time, and my future was quite uncertain. And then last year, INSA brought out a book. Archana Sharma and K.S. Harshita, they were the editors, and they took our input and they wrote these biographical essays. And this is Women Shaping Scientific Frontiers, and in which they only gave this title. In my article, they gave the title Driven by Wonder, Shrubhavati Goswami's Lifelong Exploration of Science. So, coming from a stage where this was around maybe 2000, 2001, like that, when I was writing, and this is around 2023, 24. So in these 20 years, like when I was 20 years ago, I would not even have thought that, there will be a possibility of a lifelong exploration in science. So overall, I think that it's an interesting journey, and, sometimes at the end, what matters is the what you achieve. Like, then you forget that, those struggles were real actually. Now if I think back, then I don't know how I managed. That's what I think. And because it's also a Women in Physics series, I lecture for women, I thought that I will mention that there are many, many women who are working in neutrino physics in India, and this was also boosted very much by the India-based Neutrino Observatory, although it didn't materialize. And these are all our generation, and these are our next generation. So there are many women who are working in this field. And also, I wanted to mention about the Gender in Physics Working Group. So I mentioned to you about my struggles, like, how I struggled to get a job with my daughter, because there were issues like where your husband is, you don't get a job, and where your husband is not there, then they will say you will not stay. So these kind of things happen. And then I thought that it's my problem because, I have chosen to have both. But later, I realized that even our PDFs, our students, or even the younger generation is facing the same two-body problem and other problems. So then I realized that it's actually a systemic problem, not an individual's problem. And then I was very interested to do something about it. And through Rohini, I was led to Projwal, and within the under Indian Physics Association, they established the Gender in Physics Working Group in 2017, and I was a part of it. And a brief history of the efforts of, this is not an individual's effort, there is a whole history, and that history is can be found in a nice article by Sumati Rao in one of the articles in Physics News. So that history is depicted, and Gender in Physics Working Group is still very much active, and we are organizing a lot of sessions on for young women on confidence building, imposter syndrome, then career guidance. We also organize conferences and lecture series. We also have a lecture series which is called Pavinari Padartha Vigyan Ki Narya, where we were talking about people whose work was not never acknowledged, like people talked about Anna Mani, then Lisa Meitner. So that's also a lecture series that we are considering. And I thought that, I also take this opportunity to mention little bit about Indian Physics Association, which was founded in 1970. And we have, members from all over India. And there are about 5,000 live members now. And IPA organizes a lot of special lectures and seminar. Young physicists meet, theme-based meetings. There are awards and a special lecture. Then also IPA liaises with many of the international bodies like APS, IOP. So there are lectures with IPA, IOP lecture, and with APS also, IPA members get for APS conferences, get the APS rate. So we are also doing a membership appeal. So I thought I will show this slide that please become a life member, and that will really, bolster the activities. Thank you.
Thank you, Professor Goswami, for nice talk, and especially for the last part. And from the beginning, I mean, the cartoons and everything made it very attractive. And now it's open for question and remark. So anyone has a question, please raise your hand and ask question.
Yeah, I'm Joy Khatak. That was a very nice lecture, and I really enjoyed it. I was out for about 7 minutes or so. I wanted to know from you, what about this Kolar gold mine experiments in India? Did you mention that in your lecture?
So, I mentioned that the atmospheric neutrinos, the first detection was in South Africa and in India in Kolar gold mine. First detection, but then the gold mine was stopped.
Is it still active?
No, it was, it was closed by that mining company. And but then we planned INO, but it didn't take place. It was closed, so it is not active. It has water inside.
So before we move to the next question, I just want to remember that Archana Sharma was also a speaker in one of this. She delivered one of the first few lectures in the series. And I asked Rohini to speak, and Rohini told that I don't want to speak online. I will come and physically deliver the talk. But it could not happen. Means when we discussed just after a few months, means somehow, unfortunately, we lost Rohini. But I believe there are more questions, and we move to the other questions. Please, anyone who has a question, unmute yourself and ask.
Can I ask
Yes,
a
yes,
question?
please,
Oh,
Usha.
hi, Usha. Nice to see
Hi,
you.
hi, Shiva. It was really a wonderful lecture. I enjoyed it so much. So I want to catch neutrino. But anyway, so you said you can't catch. So anyway, this is a question, and I teach particle physics in university. So I teach them with up to what is 3 flavors of neutrinos and things like that in
Okay,
general
okay.
nuclear physics. I was wondering, with neutrino oscillations, how does one now teach about lepton number conservation? Just as a elementary.
So, you know, neutrino oscillation is violating lepton flavor because nu E is going to nu mu. So that is lepton flavor. Lepton number is actually violated, means it is conjectured that it can be violated in a process called neutrinoless double beta decay, where you know where the process goes as the nucleus goes to a 2 state, like the beta decay is not energetically favored, so it goes to 2 beta. So 2 beta nuclear processes are observed. But if lepton number is violated, then there can be, it is a rare process where there will be no neutrinos. But with neutrino oscillation, we already know that lepton flavor is violated, but lepton number is not. But on the other hand, neutrino oscillation say is neutrino mass, and the most popular models to give neutrino mass are models where lepton number is violated. So they are all interlinked. And also, there is a observed matter-antimatter asymmetry in the universe, otherwise we won't exist.
Okay.
And that can also be related to the lepton number violation. And that can also be, people try to connect it also with, in some sense, with oscillation. So all these are very related.
Yeah. Okay. Thank you. Thank you very much.
Hi, ma'am. This is Guru Prasad. I
Hi,
have
Guru
one question.
Yeah.
Okay, so maybe I'm missing something. So this neutrino oscillation involves all the 3 flavors, right?
Yes.
So, and you have these 3 new lepton generations.
Yes.
And we also have 3 quark generations. Is there
Yes.
a correlation between these generations? Why I'm asking this question is because in the neutron oscillation, all the 3 lepton generations are involved. But when you do an experiment, you have only first generation of quarks involved. So does that matter? I mean,
Like in quark, you have K0 bar oscillations, right?
right.
And actually, when Pontecorvo proposed neutrino oscillation, he thought that there should be a lepton quark symmetry, and so he proposed the neutrino oscillation. So there are, because we can't have isolated quark, so there is a subtle difference between the K0 bar oscillation and neutrino oscillation. But charged leptons don't oscillate because their mass is so heavy that their oscillation wavelength is such that it's quite big, so they won't oscillate. Only the neutrinos will oscillate, but the oscillation is also observed in the quark sector in the K0 bar, B0 bar.
No, what I'm asking is, does that matter that neutrinos, when you do an experiment involving only first generation of quarks, all the experiment involve only first generation of quarks, but
No,
the
B0 bar oscillation may involve other quarks.
quarks also. Okay.
Hello, ma'am. This is Indrani.
Hi, Indrani.
Yes, I just wanted to ask you that in your slide somewhere it was mentioned that there are studies in quantum foundation and neutrino oscillation.
Yeah.
So can you please briefly comment on the quantum
Yeah, I can only
entanglement and
comment because I have not worked on it so much.
Okay.
But, first of all, in neutrino oscillation is a quantum mechanical process. We have a superposition of state which is evolving. So what people try to do is to see that whether this quantumness can be tested in oscillation experiments. So there is an accelerator-based experiment called MINOS in Fermilab, and that they have done some analysis to probe this Leggett-Gork inequality. And to see that, whether that is violated in the neutrino oscillations and whether they can have some quantumness, and they found it. But not
Okay.
all experiments found it. Minos has found that there is a violation, and then that shows that there is a quantumness. So these kind of studies people are doing. People are also doing some other kind of studies, like, there are paper where they are taking this oscillation and trying to implement it in a quantum computer. Then there are also studies related to entanglement, but I have not worked much on that. Like neutrino oscillation experiments give some bounds, that part I know, but
Okay.
now also it is picking up because of, with this boost in quantum and all, so it's picking up. So I really thought I plan to do some more study in that direction.
Okay, ma'am. Thank you.
Any other question? You have any other question?
Ma'am, just one question.
Yes,
Yeah.
please.
Guru Prasad. Okay, so one more thing that you mentioned is कि heavier flavor lags behind and a lighter flavor actually speeds up. So why is that?
There's just a group velocity, like.
Okay. Yeah, it's a group velocity, so that's why. Okay, yeah.
So I just want to make a unrelated comment. Guru is lately taking a lot of interest in quantum foundation.
Oh, okay.
So, and that when we meet physically, then we can discuss those things. Or
Yeah, that will be good,
or Guru visits
When
PRL.
Guru joined PRL, we planned that we will work together, but it never happened.
Yeah, it unfortunately it could not
So
happen.
if it can happen, it will be good.
No, and actually we are also doing some work on the neutrino. Actually, there is something called the spread complexity in the context of neutrino. So we are also doing that. So maybe if we do some good progress, then maybe I'll think of giving some talk at PRL as well. Then we may discuss some.
Please.
So any other question? It seems it's not. So every good thing ends at some time. This was a very nice talk.
Thank you
And
so much.
I would like to thank the speaker and also all the participants who not only listened, interacted also. So thank you all, and I'll expect you to join in the next meeting also. So I stop the recording and the telecast, and we'll stop the meeting. So you may. So thank you all,
Okay.
and
Bye.
we'll send the
Thank you.
notice of the next talk soon, and we'll hope that you will join.
I should stop.